So this part is on how shaft components are secured to the shaft. One of the ways is to use set screws. Okay, so set screws are things which you usually you screw them in, and so in the shaft there is there's like a thread which you drill through, and so that you can basically use a set screw to hold on to whatever shaft component you want to the shaft through using the set screw. So these are some of the set screws which I took from the book. A bunch of them. I don't really have anything special to say about any of them. When it comes to choosing some of these set screws, there is a seating torque and holding power, and I think you should know what these things mean. And so for that, what we need to do is we need to sort of analyze a set screw. When a set screw is tightened. And so what I'm going to do is I'm going to draw a top view. Or the front view. This is a shaft. Okay, so that's a shaft. And what I'm going to do is attach the shaft to a collar. So a collar is just one of the many things you can attach using a set screw. Let's try with a different color. Red. Okay, looks centered. Okay. So this is our shaft. This is the collar. Okay, and the set screw is okay. So it's one of these things. It's basically set there such that it can hold the collar against the shaft. So assume that this whole thing is torqued. Okay. So remember that the purpose of set screw is to hold things when they are torqued, not really to take action loads. Action loads would be loads which you see in this case in the plane of the paper. We're not designing the set screw for that. And the way the set screw holds on to this, or rather keeps this sturdy, is through a force. That force is a holding force. Okay, and then assume that this diameter is capital D. Okay, so all you need in order to find the torque, compute the torque is capital F times T divided by 2. Right? So this F is a specification. So what you'll do is, if you're given a torque, external torque, and you know the diameter of your shaft, you will then compute F. Okay, you will compute F, compute from T and D, right? So T comes from your application, D comes from your design, and once you know F, you go to this table. Okay, this says power, but it's really force. And based on what force you want, you'll choose the right set screw. That's pretty much what.
Professor, I have a question. If the F is in middle of the two values, then what we have to do?
You'll obviously choose the lower of the ones, right? So for example, if it is 300, so your set screw needs to hold a force of 300. So you'll use the higher of the two, right? So you'll use 385, because if you use 250, then it'll get crushed. Just like diameters, if you have if your diameter is lower, is something not in the spec sheet, you choose the higher diameter, because if you choose a lower one, your factor of safety goes down. So
makes sense. Thank you.
Choose higher. Okay, so that's pretty much what is there for set screws. Here's another way to connect two things on a shaft, like whatever you want on a shaft. So these things are called keys. Okay, and this is showing how the key is really attached. It's basically a shaft, which is the inner one. The outer one could be a collar. And then you basically make a keyway inside the shaft. Maybe the diagram is here, so you can see this. This is actually a type of a specific type of a key, but there is basically a groove inside the shaft. So for example, the shaft, this is the shaft. What you'll do is you'll make a keyway. So such that this key, any of these keys will fit inside this, but you'll ensure that it fits only half of its height inside this. The other half goes inside the collar. So you can see this. Some of it is inside the shaft, some of it is inside the collar. And that way you can hold things together. So this is one type of key: square parallel, flat parallel, tapered key, give head key. The reason why you want to have a head is because it's easy to remove by just pulling onto this part. Round key, profile key. This is a Woodruff key. So the advantage of, there's a specific advantage of Woodruff key. It basically, one of the advantages is that it has a higher depth, and that basically prevents overturning, as it's written down here. The issue with putting something so deep is that it basically weakens the key. So each of them has its own advantages and disadvantages. So even though this one is prevents overturning, it weakens, and these keys don't quite have that much force in holding. So there's always a compromise. Okay, so what we'll do is we'll go a little bit more in detail with keys. Okay, we'll analyze a key for force transmission due to tension and compression, crushing, and then use that for design. So we're going to analyze keys. Okay, so let's draw a shaft. That's the axis of the shaft. And then we have a key, which say goes in here, this groove. Okay, so that's the side view. If you look at it in the front, then all you'll see is a rectangle. Assuming it's a flat parallel key, and let's assume the dimensions are the width and the thickness. Okay, so this key is going to be subjected to forces like this. This is FT, FC. So what are these forces? FT is the force due to transmission torques. Okay, this is the torques which are being used to transfer from the shaft from the shaft could be, for example, one gear to another gear placed on the shaft. And then there is FC, which is the force due to fitting inside the keyway. Okay, now this force, which is Ft, as you can see, it's basically compressing the key along its length. So this leads to compressive force. Okay, you can see that Fc also leads to a compressive force, but this is understood to be more like a crushing of the key. So it'll crush the key onto itself if that force becomes large. Now, it's usually not easy to determine Fc because Fc is, there's no real, it just depends on the fit, right? If it's a tight fit, then there'll be higher compressive stress. If it's a poor fit, then there'll probably be no Fc and then the key can come out. So Fc is difficult to determine. On the other hand, Ft can be computed from the torque. Okay, so what we'll do is I will derive an expression for the strength in the shear strength of the key. And the shear strength is only because you need shear strength because there's Ft, which is basically trying to shear the key. But then Ft also leads to a compressive. So there's a compressive strength calculation too. So we'll do that. And those are the two important things we need in order to choose a key in an application. So let's derive those expressions. Okay, so assume there is a So okay, that's a shaft. I'm just going to show the key without the color. Okay, so the side view of this key is something like this. Where this is the length, and then this is the width. And this is the thickness. Okay, and then assume that this is the diameter is d, so the radius is half of d. Okay, so because of the force Ft, which I shown earlier, there will be shear force, shear stresses like this. And those shear stresses will cause a complementary shear stress in the other direction, as I've shown. Okay, so let's now try to write a formula for shear stress. Shear stress is force, it's the shear force in this case, Ft is the shear force, divided by the cross-sectional area over which it acts. So the cross-sectional area is the topmost spot. So that area is, oh, sorry. Yeah, something is. Yeah, my bad. This is not the one. Okay, so the shear force should be this area. And then the torque is Ft the times the radius, so d divided by 2. Okay, so what we can do is from these two equations, we can eliminate Ft. And so we get Lw tau equals 2t divided by d. Okay, and then we have a formula for shear stress. It's 2t EW. Okay, I'm out of time. I'll see you next time. We'll do this and then solve a problem. Usually you don't have thickness in this way, so I just make that W on top. And then this should be T. Okay, so that's a key in a keyway, first of all, a groove or a keyway in a shaft, and then there's a key. And the dimensions are shown. I said there are two forces. Ft is the force which comes due to the torque, and Fc is a crushing force because of the way the key is put inside the keyway, and that force is usually difficult to determine. Okay, so both forces will lead to crushing. We were analyzing this, and again, I did the mistake here. It's This is thickness, and this is width. Yeah, so and change one more thing, and then we all set. So it's the shear stress is the shear stress on the top or any layer which is along the top surface. So what we did was we're trying to derive an expression for the shear stress. So that is tau, and that there'll be a complementary shear stress due to just to keep the thing in equilibrium, so that the torque should appear in as a complementary pair. Okay, so here we have an expression for shear stress just from definition. Force divided by cross-sectional area in the yellow area. Can also find an expression for the torque based on the force and the diameter of the shaft. And then what we do is to get this expression, we just eliminate Ft in the two equations which are starred. And so we get an expression for shear stress. So that's the shear stress. That's one important consideration when we are looking at a key. Next is what else this force would do. Besides shear, it will tend to crush the key, or it will lead to a compressive stress. So we can also look at the compressive forces. So let's look at that. And we all set. Okay, so here we have a key. And the way this key is placed inside a keyway is half of the keyway is in the shaft and half of it is outside. So the part which is going to be crushed is going to be, we're going to assume that's halfway. So it's just half of it is going to be under compressive stresses. So again, this part, let's assume is half of the thickness, and the force of compression is as usual. So I call it Ft because it's the force which comes due to the torque. And then what do we need? We need the length. And I think that's it. So this leads to a compressive stress. Okay, so let's write an expression for the compressive stress. So sigma C is compressive or crushing stress. Okay, how do we do this? Well, first of all, the stress sigma C is going to be the force divided by the area over which that force acts to compress this. And it's in this case, it's going to be, you can see the cross section is the yellow area, length times T divided by 2. And so we have Ft equals sigma C T divided by 2. But then we also know that the torque is Ft times T divided by 2. So this is just the shaft Ft, the torque, that's T divided by 2. So it's basically force times distance, and the distance is from the center. So let's take 1, 2, and eliminate Ft from 1 and 2. And so if we do that, we can get an expression for sigma C. So let's just do it. sigma CLT divided by 2 equals 2T divided by D. So sigma C equals 4 times T divided by D, L, and D. Let me just have a number for this one. Let me call this, call that number 3, and then one number 4. So from 3 and 4, you can see how the crushing stress and the shear stress are related. So you just take the ratio of the two. So sigma C divided by tau equals 2 times W divided by T. So if the width was the same as the thickness, then the crushing stress is twice that of shear stress. Okay, so depending on the, of course, the dimensions of the key, that is true. So those are the two important stresses: shear stress and crushing stress. So let's see. Well, just before we start a problem, we can also define a factor of safety for keys, just like we have factor of safety for shafts. Let's define those and then do the problem. So design factors, and a factor of safety when you are done with the design, right? Design factor. Okay, so there are two design factors, one for crushing, based on crushing strength, one on shear strength, and you'll use the one which is going to be the lower of the two as the final one. So based on crushing strength, we can write SY divided by sigma C. So now I'm just going to substitute the formula for sigma C from the previous page, 4T divided by D times T times L. I believe that was equation 2. Quickly check that. 2. Oh, sorry, it's equation 4 and then 3. Okay. From 4. And so we can write N equals SY D T L divided by 4T. And then we have the shear strength, the factor of safety based on shear strength. That's simply N equals the shear strength, which is going to be denoted as SSY, divided by the shear stress. SSY is given, and then the shear stress in this case was computed to be 2 times D divided by EWL. So that comes from number 3. Okay, so we can now write an expression for N. SY EWL divided by 2T. Okay, now there is actually an expression which relates SSY with SY. So this comes from distortion energy theory. And this is something which I've done in the past. I've shown how this is true. You just have to relate the shear sigma with tau. There's a simple relationship. It's I think half, sigma is half of tau. And then from that and from distortion energy theory, we can compute the relation. It's SSY is 0.577 SY. Okay, so don't worry about that, remembering that, but I'll give it to you.
So Professor, just want to confirm, if SY is given, so we can find SSY from this formula, right?
Yes.
Thank you.
Okay, let's do a problem. Okay, a shaft of diameter it's one, whole thing is 1/7/16 of an inch. So I did the conversion for you. It's 1.4375, just to 7 divided by 16 and add it to 1, it's 1.4375. We'll have a 3/8 inch square key. So square, that's important. Compute a suitable length for the key. So the length is unknown. Assume that the yield strength of the material of the key is 54 kpsi. So that would be SY is 54 kpsi. We're given the torque 420 LPF dot in, and the design factor ND is 1.5. Let's call it N. Okay, so there's something else which is given. Diameter is given. I should put that in. 1.4375, and of a square key, which means that is this is our width. That's the thickness. With the square key means that this thing is a square. And you can see that if that should be true, then the width should be equal to the thickness, and that is 3/8 of an inch. Yes, as I said, you need to compute the length. And so given the factor of safety. Now, if you go back and look at the formulas we derive, there's a formula for crushing strength. That's the factor of safety, assuming that's going to fail in crushing. And then there's another formula for shear strength. So assuming it's going to fail in shear. Before we design this, we don't know if it's going to fail in shear or crushing. Now you might know that, because so one way to do this is to first figure out which of the two stresses are the bigger one. Whichever is the bigger one is that one is going to be the more critical one, and use that to design L. That's one way to do it. The other way to do it is to not assume that and just not to do the calculation, but just design based on failure in crushing, design based on failure on shear, get two length values, and use the larger or the bigger of the two values, just like we did it for diameter of shafts. So let's take that approach, because that approach is more direct and it doesn't, it's less error prone. Okay. So here's what we'll do. Design based on, let's pick one, crushing, let's crushing strength. Okay, so the formula I wrote down for N based on crushing was SYD times T times L divided by 4T. So here, as we'll see, we are given SY, N, D, T, capital T, and then L is unknown, so we can solve for that. So we have L equals 4TN SYDT. T is 4200, N is 1.5, SY is 54 kpsi, and 54, and so let's convert kpsi to psi. D is 1.4375, and T is 3/8 of an inch. Okay, so since all the units are now in inch, IPS, we can compute L in inches. So L comes out to be 0.866 inch. Very short key. Okay, so that's our answer, but that's not the final answer, because we don't know if the key will fail in crushing, or which of this is the critical one. So let's then compute the length by basing our design on shear stress. So design based on shear strength. Okay, so for that we would need SSY. So let's just compute that. It's 0.577 SY. That's the first thing. Other thing is the factor of safety, design factor is SSY DWL divided by 2T. I just copied the formula from the previous page. Okay, so again, N is known. SY is known because now we can compute that based on SY. D is known, W is known, L is unknown, and T is known. So let's solve for L. 2 times T times N, SY, T, W. So 2TN. I'm going to sub in the value for SSY, 0.577 SY, D times W. Okay, let's now put in the values. 2T is 4,200. N is 1.5. SY is 54. KPSI is 1,000. D is 1.4375. And finally, W is 3/8 of an inch. So we have L equals 0.75 N. Okay. So we have So just put it this way, summary. Design based on crushing strength gave us 0.866 in. Design based on shear strength gave us 0.75 in, and we have to choose one of them. So if you use 0.875 and design this, you will see that the factor of safety, and then put that value for the length in the first part, that is based on crushing strength, you will see that the factor of safety will actually come out to be less than 1.5, which you don't want. That's why you need to go for the larger of the two ones. So choose larger of the two. So we have L equals 0.866 in is our final answer.